Okay, so last time we finished strain and compatibility concepts. So this time we will continue with stress and equilibrium. And once we cover stress and equilibrium, then we are in pretty good shape to go ahead and solve relatively complicated problems. But even towards the end of stress and equilibrium, this small topic, in fact, towards the end of this lecture, I will be able to solve you a demonstrative problem. Okay, something that is actually interesting and that sort of demonstrates why we need stress and we need to consider its equilibrium. Okay. All right, so let me, as I always try to do, begin with trying to remind you what the stress was based on what we've learned in 231 and 232. So we have the stress. It's a it's a matrix. And now I'm going to express this first in Cartesian coordinates. Okay, and eventually the ideas hold in a relatively similar manner in other coordinate systems as well. So we have the diagonal components, right? The normal stresses. Sigma 1, 1, 2, 2, 3, 3. And then we have the shear stresses. Sigma 1, 2, 1, 3, 2, 3, 3, 2, 2, 1, 3, 1, 3, 2. Okay, and so these are the normal components. And here we have the shear components. Okay, so just a notational update similar to the strain. In the past, we used to write the matrix as follows. For instance, I would write only, well, in Cartesian coordinates, I would write sigma x, sigma y, sigma z. And so now just we've done this in strain. We've updated this notation to 1, 2, 3. And for shear components, for strain as well, we used to have a special notation. For stress, it was tau, tau xz, tau yz, etc. And now I'm using the same notation for all components of the stress. So this is our now slightly updated notation. Okay, so this is the matrix representation of the strain stress at a point, right? So remember, it's defined at a point, but we also had a geometric representation. And for the geometric representation, we imagined a cube. This cube is actually extremely small, infinitesimally small, and it represents what is going on at a point. So let us call the coordinate directions x1, x2, x3. And if you recall the sort of argument regarding the indices from our earlier undergraduate mechanics courses, so the idea is, well, you look at a surface and it has a certain normal, in this case x1. So the normal stress is going to be 1, 1. Okay? And now on that surface, on the other hand, there are other components of the stress, the shear ones. I'm on the plane with normal 1. And there are two directions, 2 and 3. So by default, the positive directions are these. And so I write the shear stress, sigma. I'm on the plane with normal 1, so I put 1 first, and then in the direction 3. Okay, and here it's 1, 2. Okay, right, so that's always the argument. So eventually, so this is sigma 2, 2. That's sigma 3, 3. Right? Again, I'm on the plane with normal 2, and I have a shear stress, let's say sigma 2, 3, or sigma on the plane with normal 2 in the direction 1, sigma 2, 1. And similarly, this is going to be sigma 3, 2, and that's going to be sigma 3, 1. And finally, of course, you have to remember, I take this cube, it's infinitesimally small, and this cube, however, has to still be in equilibrium, okay? So for equilibrium to occur, among other things, right? So if I take a moment about any point, let's say that corner, the moment, net moment has to be equal to 0. And based on that argument in our 231 course, we eventually concluded that the stress has to be such that its matrix representation is symmetric. In other words, sigma 2, 1 is equal to 1, 2, 3, 1 is equal to 1, 3, etc. So it's symmetric. Okay. Just like for the strain. So we have 6 independent components of the stress. Right? So let me highlight once again the notation that we have. We have the normal components, right? That would be the first index. So we are on the plane with normal xi. And the second index indicates the direction. Okay. And that interpretation holds for every component of the stress. So now I would like, so that's pretty much it. So now after this, I'm going to discuss equilibrium. But before we do that, remember when we were talking about displacement, we were trying to get a feeling for the individual components of the displacement in different coordinate systems. So I like to do the same thing once again. And eventually for that, I'll consider a number of examples. So this is a picture in the Cartesian coordinate system. So I will begin with an example in the Cartesian coordinate system. And in doing this, we will experiment with the components, but also I'll throw in a few concepts that you will recall, but we need to explicitly highlight those because they will be very important for solving problems. Okay, so the example that I have, it's a cantilevered beam. I'll try to draw it in a 3D setting. So it's something like this, right? It's a problem that we even considered in our first mechanics course, but eventually when we want to solve this problem once again in a, let's say, slightly more complete manner, we're going to revisit this setting in this course. So the coordinate system. We don't need a very precise origin, so let me just say that the longitudinal direction is x1, the thickness direction is x3, and along the height it's x2. And so we have a certain loading. That's what I impose on, just for the sake of discussion, on this beam. So I have a normal force. It is exerted, let's say, ideally at a point at the right end. And also at the top, there is a distributed force. Okay. So let's call that W. Okay. And so W, just to make things clear, W has units newtons per meter squared, and P has units newtons. Okay, so let me also label the surfaces. I'm going to refer to them. This is the top surface, and this is the front surface. And then we have the right surface and eventually the left surface. Okay. So we're going to pull, we're going to apply the distributed law. So for sure it's going to bend and it's going to extend a little bit as well. It's rigidly supported on the left-hand side. Okay. It doesn't move anywhere there. And now I'd like to talk about the components of the stress on different surfaces. Okay, so that's the goal. So I begin with the top surface, this one. So we'd like to eventually talk about the components of the stress, right? So whenever I consider a surface, the first thing I make a note in my mind is the normal associated with the surface. It's x2 on the top surface, right? So in other words, all the components of the stress event, so unfortunately my directions are different, but normal is 2. So the components of the stress I'm going to be talking about, they are going to be sigma 2, 2, 2, 3, 2, 1 eventually. Okay, so normal is associated with x2. And we have their normal stresses and, of course, shear stresses. So we are on the plane with normal 2. And I'm in the normal direction along the 2 direction. And so sigma 2, 2 on the top surface is equal to, in magnitude, w, right? But the direction of w is downwards. It's sort of compressive. And if w is the magnitude, it's supposed to be minus w. Okay, so if we'd like to express that. What are sigma 2, 3, and 2, 1? 0, because there's nothing, right? So if I somehow applied something in the tangential direction, somehow something like friction, then there would be a perhaps non-zero component. But presently, it's 0. Okay, so now let's proceed with the left surface. So the left surface is where the beam is attached to the support. And there the normal is, well, I don't directly care about the direction of the normal. I only care about the fact that it's along x1. Okay, so on the left surface, it's along x1. So it's minus x1, but I will just write x1. That's what I'm concerned with presently. So there again, we have normal and shear. So I'm on the plane with normal 1. So I'm going to be looking at normal is 1, 1, and then there's going to be a 1, 2, and a 1, 3 component. Okay, so now we'd like to figure out if anything is 0. And if it's 0, it's good to be able to recognize that. Okay, it might simplify our lives. So on the left surface, let's imagine what's happening. So first of all, is there a normal stress on that plane? Well, if there is no normal stress, there is nothing that can balance this normal force, right? So there has to be, for sure, a sigma 1, 1. Well, is there a stress that forms in the 2 direction, or in other words, sigma 1, 2? Well, if there is no such thing, nothing will balance the net force that's due to that. So for sure, this is also not going to be 0. Now, is there a 1, 3? That's perhaps tricky at first sight. Well, but you can imagine that I'm trying to deform this thing, pull at it. So eventually, perhaps due to Poisson effect, is trying to, let's say, contract along the 3rd direction due to deformation, but I am constraining that deformation, right? It cannot contract, and to resist that contraction, there needs to be some stress. So even this is possibly non-zero. So I cannot say from the outset for sure that any of these are non-zero, okay? So possibly this is also non-zero, but the other two, for sure, I'm very confident, let's say, that they are non-zero. Okay. Now, but that is quite not the only thing I can do, sort of eventually to help myself solve the problem a little bit better. And essentially what I can also do is I can impose static equivalence between these stresses and the loadings that I see on the structure, okay? So that's sort of a requirement. It's something eventually that I will have to use when I'm trying to solve the problem. Okay. So static equivalence requirement on the surface can be imposed as follows. Well, I have three directions, right? I have the x1 direction and the x2 direction and the x3 direction. And the net force that is forming due to the stress distribution on the surface along each of the surfaces has to be equal to, statically, to the net forces that I see on the original problem, right? So this is at least something we can write. So for instance, I'm integrating on the left surface, right? The left surface is, again, perhaps I should have made it a bit more clear. Right? It's this surface on the left. Okay, so if I integrate on that surface sigma 1, 1, I should get P, okay? And if I integrate sigma 1, 2, assume that W is a constant. So it should be equal to, by static equivalence, it should be equal to minus W times the area of that surface, whatever it is. Okay. I'm not looking for equilibrium, right? I'm looking for equivalence, static equivalence. Okay, so the signs are the same always. So minus W times the area, assuming W is a constant. The area is the area of the top surface. So let's make that clear. Area of top surface. And sigma 1, 3 is possibly non-zero. But there is no net force in the third direction. And so even if it's non-zero, when I integrate, it should integrate to 0 for sure. Okay, so I gave an example for the plane with normal x2, x1. Let's pick a plane with a normal x3, which is, in this case, let's say the front surface. So I'll add that here. On the front surface, the normal is associated with x3. And again, I have a normal stress component and two shear stresses. The normal is sigma 3, 3, and the shear ones are sigma 3, 1 and sigma 3, 2. But on this surface, I'm applying absolutely nothing, and therefore every component of the stress is equal to 0. Now, if you have a surface on which every component of the stress vanishes, such a surface is called traction-free. Okay, and that's the terminology eventually that we will make use of. So it's a traction-free surface. Okay, right. So that's an example in Cartesian coordinates. Let's then proceed with an example in spherical coordinates. Okay, so example in spherical coordinates. Okay, somehow I have, let's say, a sphere. This is an example that I previously sort of discussed. Let's say that it has a thick wall and it's hollow on the inside. So I'm taking a cut in that direction. And that's what we see, right? And there is, let's say, an internal pressure, Pi, and there's nothing on the outside. Okay. Now I'm going to take one more cut let's say like this. And I'm going to draw that cut over here. Okay, so that's another cut. So this is that's the red cut, and that's the, just to make things a little bit more clear, that's the green cut. Okay. That's 1/4 of the sphere. And I'm going to look at two surfaces, right? One of them is the top surface, and the other one is the right surface. Okay. And let's consider a point. Let's consider this point here. Now the coordinates, or the vectors for a spherical symmetry, it's always a bit hard to draw, but in this case, I picked sort of a special point. This is sort of the center, so the ER direction faces outwards, okay? And then there is a tangential direction, E theta, and sort of the normal to the top surface, in this case, would be E phi. Those are the three basis vectors that we would have, okay? And so now, let us look at the stress components. Okay, so we have the inner surface. The inner surface, by inner surface, I mean where the internal pressure is applied. So in practice, maybe I've said this before, so of course there will, in general, be a pressure on the outside. But just for the sake of simplicity, I've assumed that that is equal to 0 in this case. So I'm just concerned with a simplified example, also to demonstrate eventually a traction-free surface. So on the inner surface is this inner cavity. Okay, that's one surface that we have. So that is a surface with a normal in the R direction, right? And we have a normal stress component and a shear stress component. So I'm on the plane with normal R on the inner surface, so it's going to be a sigma R in every case. And the normal stress component is RR, and then I have a R theta and a R phi. Right, so is anything 0? Are we clear about the surface I'm talking about? Right, so I'm looking at this surface, the inside cavity, where there is a pressure. Okay, so so the normal stress and the shear stress components. Anything 0? The shear stress is R0 because there is nothing acting tangential to the surface on the inner surface. And the normal one, it's magnitude-wise pressure, but pressure is compressive, so it's minus Pi. Okay, let's look at the outer surface. The outer surface is also related to R, but now that surface is easy because there is nothing tangential or normal to it, so therefore the outer surface we can say is traction-free. So we don't need to essentially, that's eventually, the fact that it's traction-free doesn't mean that we don't need to do anything. We will also make use of that information, the fact that it is traction-free. Okay. All right, so let's proceed now with the top and right surfaces. So let's go to the top surface. So the top surface has it's a it's the green plane, so it's with a normal E phi in this case. Right. So there is going to be a normal component and a shear component. So sigma phi, sigma phi, sigma phi. The normal one has the same index, and then sigma phi r, sigma phi theta would be the shear components. Okay, so is anything zero? So remember what the pressure is trying to do. The pressure, since we're talking about the top surface, you can look at this picture. Okay, the pressure is trying to split this thing apart. And what needs to hold it together are the stresses that form on that surface. So for sure, something is non-zero, but is anything zero? And let me, as a way of sort of comparison, I only have internal pressure. What I could have also done is, there could be the internal pressure, and additionally, I could take the sphere and suppose it was some sort of a container, and I could be trying to open it. I could be applying some sort of a torque on it about this axis, okay, something like this. I'm not doing that, right? So the pressure is trying to make this thing expand. This one, non-zero. So that component, let's draw that component. So this is, I would like to take time and sort of talk about these components because eventually, perhaps, let's say we can improve our sort of perception of the problem. So these are not so straightforward. I mean, eventually when we solve, we will, for this problem, for instance, we will start with the displacement. And we already discussed this example. In this example, the only non-zero component that we will be talking about for displacement would be the r component, not theta or phi. Okay? So when you start with that, actually, you immediately see which ones are zero. It automatically comes out. You don't have to worry about it. But let's see. Okay, so on the plane with normal phi in the direction r. That would be, for instance, at that point, that would be the stress. Okay? So perhaps it's not so clear. So that would be sigma what? Phi r. And this would be sigma phi theta. Okay? So for instance, when I torque this thing, which component would be non-zero? Phi theta probably, right? Now, phi theta, if I torque it, would be non-zero. So I'm not torquing it. Do we agree, for instance, that phi theta is probably zero? Okay, because I'm not torquing. Okay. Do we also agree that the normal component, so if the normal component is zero, what is it that's going to balance the net force that is due to the pressure that forms in the phi direction? It's trying to split this thing apart. Something has to pull this thing back together, right? The two pieces together. So the normal stress cannot possibly be zero. So the normal one, it's not going to be zero. I'm not torquing this, so phi theta is zero. This one is probably a little bit hard. Perhaps you could think, and rightly so, perhaps it's zero here, let's say, and zero there, but somehow it increases and decreases back to zero. Or let's say it increases and becomes negative, comes back to zero. It could do all sorts of fancy things. It's not very intuitive, but in this case, it turns out it is zero. If it's not intuitive for you, it's okay. This is not something we have to see from the outset. But eventually, when we solve the problem, it will come out to be zero. Okay? Perhaps at this point, it is sufficient that you are able to relate the components and the directions of the stress. So let's look at the right surface. The right surface is the one with normal. So the normals change from point to point, right? So on that right surface, the tangential direction, if I come to that point, I'm following theta. So the normal direction would be E theta still. Okay. So normal on the right surface is the theta direction. And I have normal stresses and shear stresses. So theta, theta, theta r, and theta phi. Now, here essentially we've done the discussion once, right? So if I take a cut like this, the normal is theta. If I take a cut like this, I'm sorry, I repeat. If I take a cut like this, the normal is phi. If I take a cut like this, the normal is theta. You turn it over, one picture, turn it over, you get the green picture, sort of. So the pictures for phi and theta, they are really the same pictures. So the same arguments also hold. In other words, there has to be a normal stress because the pressure is trying to split this apart, and something needs to hold it back. There needs to be something that resists the tangential stresses. So sigma, well, eventually, I'm not applying any torque, and you just need to, at this stage, believe that the other shear component is also 0, okay? Because there is some sort of symmetry between the theta and phi directions. Both directions are tangential directions. In fact, eventually, by symmetry of the problem, right, there is nothing that sort of puts more emphasis on the theta direction than the phi direction. The problem is entirely symmetric. So by symmetry, in fact, from the outset, you could also say that the only non-zero components, theta, theta, and phi, phi, are actually equal to each other. Okay? This is something we could expect, right? In fact, all of these things are things at this stage that we can expect. So if you don't see it, it's okay. But at least you should feel comfortable with what, let's say, that component means or that component means. The normal and the direction you should be able to sort of figure out. Okay? All right, so and as I said, eventually when we solve this problem, we're going to use the displacements and we will immediately see which components are 0. All right, so let us go to another problem. So I've done the Cartesian coordinates, the spherical coordinate system, and now we'll have a look at the cylindrical coordinate system. So an example in cylindrical coordinates. So imagine this almost to be a piece of your good old wooden pencils. Okay, so he's using 2 of those. Okay, so inside there is the lead, and outside there is the wood part. The lead is so much stiffer than the wood that let us say that the lead is rigid. So I'm not going to worry about the displacement of this thing. And now eventually when I press on the surface, there will be a force on the lead. It will try to push the lead inside because you're applying a force to right? And you're holding from the outside, okay? So I'm simplifying that problem, okay? Writing on a piece of paper with a wooden pencil. Okay, so the outside is fixed. That's where you're holding, and you're pushing on the surface. That applies a force on the inside inner cylinder, and that's rigid. P on rigid cylinder. Okay, so I just put a tensile force. Okay. All right, so fixed means, by the way, that displacement is going to be non-zero. So the outer surface of the cylinder is entirely fixed. It doesn't move anywhere. On the inside, I am pulling with a force P. So somehow this, and on the left, it's free, okay? I have nothing. And so when I pull, this inside rigid cylinder is going to try to move outwards. I'm holding it fixed. So this surface and the material inside somehow needs to partially move with it. So it needs to deform in such a way that so perhaps something like this. I don't know exactly. But if I were to take a cut, it's fixed on the outside, right? So I've taken a cut like this, right? You're pulling on the inside, so this is the type of deformation that you would have. So, by the way, which component of U is for sure zero in this problem? Let me pick coordinates for, well, actually the coordinates are rather clear. There's the radial, tangential, r, theta, and the axial one is going to be the third direction. So as I draw that once again, think about which component of displacement is for sure zero. So which component of displacement would be zero in this problem? Well, the outer surface is fixed, yes. So I'm pulling on the inside, right? So the inside will try to move when I take this cut. So there is for sure some displacement. The outer is zero. But I'm talking about the components UR, U theta, U phi. Is any one of these, and one of these is for sure, from the outset zero. Ah, that's good. It's not very easy to see. The displacement in the radial direction, it's in that direction. So he's saying it's zero. Actually, it is true. It's zero. Okay? But what else is zero? Theta, because I'm not trying to torque this thing. If I try to torque it, theta would also be non-zero, but it's zero. So you see, actually, he said that. It's interesting because in this problem, if I'm not torquing it, I said, so this component is for sure zero, but it was not clear whether this component of the stress was zero, right? It might not have been, but it is. So actually, in this case as well, immediately by looking at it, perhaps the radial direction is not zero, but it is. Okay. So the two components are zero. You only have to worry about the axial component. Okay, but we're talking about stresses, right? So eventually, let me try to now draw that. So I am applying a force on the inside, right? And eventually, something will form on the inner surfaces, right? So some sort of distribution of force will form on the inner surface so as to resist the force that I'm applying. Or this force, instead of being a point force on the rigid cylinder on the inside, it's going to be distributed onto the inner surface. Perhaps something like this. Yes, you are applying the load at a point on the lead, but the lead is in contact with the deformable outer wooden layer along that surface. And along that surface, therefore, there has to be a distribution of stresses that are eventually equivalent to the force that I'm applying. OK, so let's now talk about the components of the stress. So first, the inner surface. The inner surface is the plane with normal R. And there I will have normal and shear. And the normal one is sigma RR. The others are sigma R theta and sigma R3. Anything zero? Right? Displacements perhaps are a little bit easier, right? But now we're talking about stresses. R theta, because I am not, so R theta, right. I am not applying any torque. It's 0. How about sigma R3? I'm sorry, I should have said not R3, RZ, because direction is our notation for cylindrical coordinates, it's Z. So on the plane with normal R, in the direction Z. Well, there is something. It has to form, and it has to be such that it is statically equivalent to the force that I'm applying. So statically equivalent to P. So in other words, sigma RZ integrated over the area must be equal to P. Okay. I don't say exactly equal, because there is sometimes a minus sign. We need to be careful. But it's plus or minus P. OK. So that's the inner surface. And now the front surface. The front surface is that surface. And the front surface has a normal Z, and there is nothing there. So that for sure is traction free. Okay, that's easy. And let's make also a note of your observations. You've already indicated which components are 0. So UR, U theta, UZ would be the components of the displacement we would be seeking. And you already said, well, UR is 0. I'm not torquing this. U theta is equal to 0. And so there is only UZ. Okay. When you're trying to solve this problem, eventually it would also help a lot if you could finally also see the dependence of U on the coordinates. So for instance, so this is the only non-zero component, but in general, U depends on, right, all the coordinates. So R, theta, and Z. So think about, additionally, if you could cancel some of that dependence. For instance, you could say perhaps that the displacement along that direction, that's the only non-zero component, does not depend on the angle, because the problem has some sort of symmetry. Only it's not rotating. It's only moving out. There is no torque. So for instance, right, this one you could cancel. Okay? You can cancel one more. Okay? Think about that. All right. So we're in good shape. Now, so what we've done is we've talked about the components of the stress, and we've talked about the components of the stress in different coordinate systems. So now we have just enough time to talk about equilibrium of the stress. So the stress distribution that forms in the material cannot be anything. So for instance, to say the least, you are applying some forces. The stress distribution needs to be such that it is statically equivalent to the forces that you're applying. But there is more to it, and that is associated with equilibrium. Let's do our equilibrium analysis. Now, equilibrium analysis, I'm going to do this in 2D. So in other words, again, remember, life is 3D. I'm just going to omit 3D in this case, just to simplify our analysis. This is something that you have for sure done in your thermal fluids courses when we were talking about the Navier-Stokes equations. We have not done this in the mechanics courses because we didn't need it. Okay? But in this course, it's going to be very, very important. So let us drive equilibrium equation that is associated with the stress. So here's my structure. And the structure is, let's say, somehow loaded. So there is a stress distribution, right? The stress is, in general, different at every point in the structure. Now, I'm considering what happens in the vicinity of a particular point A. And so I'm going to take a differential area element, a very small area element in the vicinity of that point. Okay? So this area, so now it's not, what I'm drawing is not really a geometric representation of what goes on at a point. It's something that is extremely small, but it has a finite size. Okay, so this is the area. Okay, and this is our point A. And this area along the coordinate directions x1 and x2 has infinitesimal edge lengths dx1 and dx2. Okay. All right, and now on that surface, on the surfaces of this differential element, there are normal and shear stresses. Let me not directly write the components, but indicate the directions. There is, of course, a normal one, and a shear one, and a shear one, normal one, and here also similar, normal to the surface. And there is one that is shear. The direction is like this, shear and normal. Okay. What I care about really is sort of how the stress changes along this differential element. Okay, so as I said, so this is a picture that is slightly different from the very first picture that I've drawn at the beginning of the course. So this is not representing what happens exactly at an ideal point. So this is a finite size, very small but finite sized area. So which means that the stress from this corner to that corner, for instance, will change because the stress is a function of position. It changes throughout the body, and therefore from that point to that point, no matter how small, it will also change. So let us call the value of the stress here sigma without referring to any of the components. Stress at point A is sigma. But now when I move along that direction, sigma will change a little bit. It is changing because I'm moving in the x direction. So the rate of change of the stress along the x direction, it is this, right, derivative with respect to x1, times the amount I move in that direction, dx1. Okay? So that is the stress at this corner. If I move up, I'm varying the coordinate along the x2 direction only. So the stress again changes, but this time the rate of change, it's along the x2 direction. So it's plus dx2. Okay. And when I move to the top right corner, it's changing in both directions, so I have to add both of these. So that is what the picture looks like. Now, in addition to that, in addition to the sort of stresses that are on the edges, so there's a stress at every point along the edge. I've only noted the values at the corners, right? In addition to these surface stresses, there is also that acts directly on this area, or in 3D, the volume. For instance, if there is gravity, the gravity will try to pull this thing down, right? Now, let's imagine a force that is more general than gravity, and let me call it F. F is force per unit volume, okay? So it is 2D, but if you like, you can imagine that there is a third direction with unit thickness. So still, I'm not going to say per unit area, but per unit volume. So that's newtons per meter cube. In the simplest case, it could be, for instance, gravity. But we will have examples where it represents, the volume force will represent something else, effectively. Okay, so that's the setup. So now that is our differential element. There are surface and there is a volume force acting on it. And this thing has to be in equilibrium. So I enforce equilibrium. Okay? So there is a net differential force acting on it. Right? This net differential force is due to the surface stresses and the volume stress. And as a result of that, this thing will, in general, accelerate. Okay? So it has an infinitesimal mass, and it will have acceleration, u double dot. Right? So this is now the equilibrium condition. So it's not static equilibrium, it's sort of dynamic equilibrium. Now this part is rather easy. dm, it's simply the density rho, dx1, dx2. If you like, and let me add this here, times unit thickness. Okay. Again, I'm not showing that. And now there is the force. Well, now I'm going to talk about the force. The force is a little bit tricky. Okay? Now the force is a sum of that and the surfaces. Now let's talk about that surface. Okay? This edge. Okay? And along that edge, I want to concentrate presently, just for a second, only on that component. This component is, in the direction 1, normal stress, sigma 1, 1. So I'm going to look at sigma 1, 1. So on the right surface, and so that is a sigma 1, 1. And the picture that I see is sort of like the following. Well, actually, it's black, so let me use black. Okay, so this is a portion of the square. Okay, and here I have the value of the stress. It's, let me exaggerate, sigma 1, 1 plus, right? So I'm looking at only the 1, 1 component. 1, 1 plus del sigma 1, 1 over del x1 dx1 plus del sigma 1, 1 over del x2 dx2. Okay? Just concentrating on the 1, 1 component. And at the bottom I have So eventually, the magnitudes are different. And so sigma 1, 1 will somehow change from that value to that value. It could, in principle, go non-linearly, but it turns out I don't really care because this distance is so small that I will assume for all practical purposes that that variation is almost linear. And now, for instance, when I talk about this incremental force, it has various components. But for instance, along the one component, for sure, sigma 1, 1 is making a contribution to that net force on that infinitesimal element. And the net force due to sigma 1, 1 along the one direction is the area under this curve, right? Okay. So now I'm going to do the same thing without drawing, of course, every time for all components of the stress in all directions. Again, it has unit thickness, but essentially I need to sum this component with that component, divide it by 2, and multiply it by the height, which in this case it's dx2. Okay? So dx2 times that plus that over 2 times unit thickness would be the net force in the one direction due to sigma 1, 1 component. All right, so let's do that explicitly. So I'd like to write the net small force in the one direction, dF1. So it has two parts. First, there is, of course, the force due to this volumetric contribution. So force per unit volume in the one direction, it's F1. And the volume is dx1 times dx2 times unit thickness. Again, I'm not writing the unit thickness. So that takes care of F. So that's through the volume. And now on the surfaces, I'm looking in the one direction. Let's begin with that surface. So I need to look at sigma 1, 1. I've already discussed it here. So the net force due to that is equal to dx2, right, divided by 2, and then top plus the bottom. Okay. So sigma 1, 1 plus, so now let me simplify my life a little bit. Sigma 1, 1, comma 1, dx1 plus sigma 1, 1, 1, comma 2, dx2 plus sigma 1, 1 plus sigma 1, 1, comma 1, dx1. If I make a mistake, and I might, just watch out and let me know. So that's due to the x1 component. And just trying to make it a bit more clear. So this is the right edge. Okay? So let's do the same thing on the left. On the left, again, I'm looking in the one direction, so there is also a sigma 1, 1 there. It varies from that value to that value. So in fact, it's simpler than that. So the direction is negative, so now this dx over 2, and it varies from sigma 1, 1, 2, sigma 1, 1 plus sigma 1, 1, comma 2 dx2. So at the top, it's sigma 1, 1 plus sigma 1, 1, comma 2 dx2. And on the right, it is, at the bottom, it is simply sigma 1, 1. Okay. So that's a little bit easier. So this is the left edge. Okay, so now I'm looking along the one direction. So that and that edge is taken care of. But now if I look at the top and bottom edges, the shear stresses will have a net, contribute to the net force along that direction, right? So this one, for instance, it is sigma on the plane with normal 2 in the direction 1. So sigma 2, 1. And here also it is sigma 2, 1. This is a plus, that's a minus. Okay, so now I have to do that. Sigma 2, 1. So it's going to be, so plus area under, so there's going to be a distribution like this, but flipped over, increasing like that, let's say. The edge length is dx1. And I'm going to sum the value here plus that divided by 2, dx1 over 2. I'm looking at sigma 21. So let's write the right one. Sigma 21 plus sigma 21 comma 1 dx1 plus sigma 21 comma 2 dx2. And on the left, it's sigma 21 plus sigma 21 comma 2 dx2. So that's top surface. And minus the bottom surface. Okay, so that was sort of the hard part. So now we can start canceling things. Okay, so if you like, don't write anything for a second. I'm just going to cancel terms, right? Sigma 1, 1, 1, 1 over 2. 1, 1, 1, 1 over 2. So these all die. They're gone. Okay, so what else? 1, 1, comma 2, 1, 1, comma 2. They die. Gone. And the only remaining one is 1, 1, comma 1, but there are two of them divided by 2. It simplifies our life a little bit. So similarly, if you look here, 2, 1, 2, 1, 2, 1, they are there. These are gone. Okay. And also 2, 1, comma 1, 2, 1, comma 1. It dies away. And what I'm left with 2, 1, comma 2, and there are two of them. Okay, we'll cancel the 2. So now I'm just writing the result on the left. Okay, and what I'm doing is I'm going back to this equation. I'm writing, right, eventually df1 equals dm, which is that, u double dot in the one direction. Okay. So df1 is equal to dx2 multiplying dx1 multiplying sigma 1, 1, comma 1, and then plus, again, dx1, dx2 multiplying sigma 2, comma 1, comma 2. Plus, of course, our f1. Questions about what I've done so far? Any question? No. All right. So all I'm going to do is now I'm going to write this a little bit more compactly. I'm going to write, instead of so many indices, slightly different. So f1 dx1 dx2 plus what I see here is a sum over one in this index of the stress. Let's call it J. The second index is always 1. And then comma J. Right? So J goes from 1 to 2. 1, 1, comma 1 plus 2, 1, comma 2. Okay? That's all I've done. All right. So moreover, I remember also, to simplify things a little bit, that this is equal to sigma 1j, right? Or the whole thing, if you like, is equal to sigma 1j comma j, because it doesn't matter if it's 1j or j1, stress is symmetric. So I've also done that so that these j's are next to one another. Hence, what I have concluded is I have df1. So I'm working along the one direction, and it's equal to dm u double dot 1. So dm, it's easy. So it's rho u double dot 1 dx1 dx2. That's the right-hand side. And on the left-hand side, I have that expression. Sum over j, sigma 1 j, comma j, dx1 dx2 plus f1 dx1 dx2. Okay, so equilibrium along the one direction. So left and right hand sides are now taken care of. And of course, this dx1 and dx2 terms, they appear everywhere, so I can get rid of those. So in other words, this thing is arbitrarily small. So then I end up with sum over j, sigma 1 j, comma j plus f1 is equal to rho u double dot 1. So I have a few minutes left, so I prefer to finish that today. We'll go a little bit over time, maybe 3 minutes. So if you now do the same thing along the two direction, right? I worked in the one direction. It turns out, similarly, along x2, you would find that essentially what will change is the first one. This one appears there because I am looking along the one direction. If you look along the two direction, you will simply find that you get the same thing with 1 replaced by 2. Okay? So that is essentially the remaining one. Well, in fact, I am almost done. I'm not even going over time. So let us wrap this up. OK, so we've done it in along the 1 and 2 directions. So therefore, now you could do this in 3D, of course, and then you will get essentially the same thing with 3. So therefore, in a general 3D setting, right? So it's 1, 2, or 3, depending on the direction you are looking at. So we can, in general, call that direction that I am looking at simply, let's say, I. I could be 1, 2, or 3. And essentially, for any choice of I, it has to hold. J is just a summation index. For 1 or 2, there's a sum over j. But for any choice of I, that equality has to hold. Okay, so in a general 3D setting, therefore, what we have is sum over j, sigma I j, comma j, plus fi is equal to rho ui double dot. And that's the result. Okay, so I've done it in 2D. I've done it along only the first direction, but then I've sort of tried to argue that it's going to be the same in 3D and along any direction. So now, however, all I've done is in a Cartesian setting. Okay? But now, if I do take one more step and observe something, then I'll get a result that holds in any coordinate system. So this thing here, it's simply the component. So what I'll try to do is, this is a vector, components of a vector, components of a vector. This thing is also a component of a vector because there's sum over j. The only thing that I can choose for all I, okay, is I. It's 1, 2, or 3, right? So now, therefore, this is plus f in vector form. This is rho u double dot in vector form. And now if you go back to the very first lecture and look at the definition for the divergence of a matrix, that's exactly what it is. So this is the divergence of stress. And this is our equilibrium equation. And it's correct for any coordinate system. Okay? So in any coordinate system, let's say in cylindrical, it would be r theta z, r theta z. And now you just have to express the divergence of the stress in the cylindrical coordinate system appropriately. Okay? As long as you do that, this expression is always true. And this is an expression that I would like you to learn, okay? That I would like you to remember. All right? So let's finish for today, and I'll see you next week.